Welcome to Oslo. We are here on this glorious June day to celebrate the finest scientific minds and the best scientific research. Hello to all of our friends around the world, and especially those in New York at the World Science Festival, which is kickstarting this celebration. And it really is a celebration. In just a few minutes, we'll be discovering who has won the Kavli prizes for 2016. Now, this is the 5th time that we have stood here, every other year since 2008. And earlier today, 9 scientists from around the world received a phone call from here in Oslo, letting them know that they had joined the ranks of the great past Kavli laureates. The prize is a collaboration between the Kavli Foundation, the Norwegian government, and the Norwegian Academy of Science and Letters, which is where we're standing right now. International committees are selected by the Academy, and they spend many months carefully and secretly choosing every single laureate. And I think we are ready to go. The Academy President, Ola Søyestad, is about to make the announcement. So let's go and hear what he has to say.
Ladies and gentlemen, this is a great day for science. Indeed, it is a great day for excellence in science. Welcome to the announcement of the 2016 Kavli prizes. Today, we are honoring great scientists in 3 categories for work that has provided us with new tools and new ways of thinking about astrophysics, nanoscience, and neuroscience. In the words of the founder of the prizes, the late Fred Kavli, today we honor the science of the largest, the smallest, and the most complex. Now, let's move on to the announcements themselves. For the discovery of mechanisms that allow experience to remodel brain function, the Norwegian Academy of Science and Letters awards the 2016 Kavli Prize in Neuroscience to Yves Marder, Brandeis University, USA, Michael Merzenich, University of California, San Francisco, USA, and to Carla Schatz, Stanford University, USA. Many congratulations to the 3 new neuroscience laureates. To elaborate on the choice, please let me introduce the chair of the Kavli Prize Committee in Neuroscience, Professor Ole Petter Ottersen. Ole Petter, if you please.
Every taste, sight, smell, sound, and experience changes our brains. Neurons make new connections with sensory experience and prune others. Our brains have a remarkable capacity to adapt to changes in the environment and to form memories. What we also know is that our personality and behaviors typically remain fixed as we pass through life. It is the elucidation of this delicate balance between plasticity and stability that we celebrate in the 2016 Kavli Prize for Neuroscience. Yves Marder used the simple neural circuits in crustaceans to elucidate the dynamic interplay between flexibility and stability in the nervous system. She identified the signals that reconfigure the output of adult neurons without altering their underlying anatomy. The work of Michael Merzenich has demonstrated that sensory circuits in the cerebral cortex are reorganized by experience in adulthood. Merzenich showed that after injury, simply expanding or limiting the use of different fingers leads to a corresponding change in the representation of the hand in the brain. He also showed that the auditory cortex changes its map of sound frequencies after individuals learn to detect fine differences in pitch. This discovery helps explain how humans can recover their perception of speech with cochlear implants. Mercenick showed that both neurochemicals as well as cognitive factors, such as attention, can determine whether plasticity takes place in adults. This work is being used to maximize learning and recovery following brain injury and disease. Carlos Schatz showed how patterns of activity in the developing brain sculpt the arrangement of synapses between neurons. Her work demonstrated that the formation of connections between the eye and the brain of mammals depends on neuronal activity before birth. She showed that spontaneous waves of activity sweep across the retina early in development, and that these patterns fine-tune the final set of connections from a genetically determined map. Her discovery that neurons that fire together, wire together, links brain wiring during development to the circuitry underlying adult learning and memory. Eve Marder, Carlos Schatz, and Michael Mercenick have unraveled how the brain changes as we develop in the womb and in adulthood, yet at the same time maintains it in a reliable state. Their work has enlightened the question of how our brains remain stable while allowing for substantive changes during development and learning. The picture of how we experience the world around us has been utterly redrawn.
And now, from the most complex to the very smallest. For the invention of atomic force microscopy, a breakthrough in measurement technology and nanosculpting, the Norwegian Academy of Science and Letters awards the 2016 Kavli Prize in Nanoscience to Gert Binnig, the IBM Zurich Research Laboratory in Switzerland, Christoph Gerber, University of Basel, Switzerland, and to Calvin Quaite, Stanford University, USA. Congratulations to the 3 new Nanoscience laureates. The Nanoscience Committee is chaired by Professor Arne Brattås. Arne, if you please.
Thank you. Sculpting with atoms has been a long-standing dream of nanoscience. To position single atoms on any surface, one by one, would enable the design and creation of revolutionary new structures. The invention and creation of atomic force microscopy, or AFM, has transformed those dreams into reality. Imaging atomic structures in a wide range of material systems was another visionary concept. Based on this technique, sculpting and analyzing nanoscale structures is now widely used in the fields of physics, chemistry, biology, and materials science. In AFM, a nanoscale tip scans across a sample surface at atomically close range. The tiny forces between the sample and the tip are detected, and these forces reveal many properties of the sample, such as the arrangement of its individual atoms, now with atomic resolution. Electric and magnetic interactions, friction, and chemical bonding can induce these forces. The technique is applicable over a wide temperature range and in magnetic fields. And crucially, atomic force microscopy can also be applied to anything, including non-conducting materials such as liquids and biological systems. Nanosculpting is a process of adding, arranging, and removing individual atoms. The tip provides an adaptable tool for accomplishing that level of control. Being able to manipulate conductors and insulators at the nanoscale has applications comparable to those of nanoscale 3D printing. The techniques can be used to control the surface of materials with atomic precision. For example, it is possible to swap atoms one by one at surfaces. Force microscopy-based techniques have created new devices in nanoelectronics, nanophotonics, and nanomagnetism. The advantages of AFM include experimenting in liquids such as water, which opens the possibility of exploring biological systems. A single molecule, such as DNA or a protein, can be suspended between the tip and surface. Lifting the tip stretches and unfolds the molecule and reveals its elastic properties. And this can be used to tell us how these biological molecules work. Similarly, temperature-sensitive cantilevers in AFM opens new doors for medical applications, enables high-resolution advanced drug design. The invention of AFM has spawned an incredible variety of measurement and manipulation tools invaluable for more than a dozen new techniques. These are already being used across every branch of science. Just one exciting example is friction force microscopy, which allows us to measure lubrication at an atomic level. Atomic force microscopy is a powerful and flexible scientific technique that continues to advance nanoscience for the benefit of society. The instrument and the many spin-off instruments it has inspired have an enduring benefit across the sciences, from physics and chemistry to biochemistry and biology.
And finally, from the smallest to the largest. For their work for the direct detection of gravitational waves, the Norwegian Academy of Science and Letters awards the 2016 Kavli Prize in Astrophysics to Ronald Graver, California Institute of Technology, USA, Kip Thorne, also at Caltech, USA, and Rainer Weiss, Massachusetts Institute of Technology, USA. Many congratulations to the 3 new astrophysics laureates. The Astrophysics Committee is chaired by Professor Mats Karlsson. And Mats, if you please.
On September the 14th, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected a pulse of gravitational radiation emitted by the collision of 2 black holes. This discovery has, in a single stroke and for the first time, validated Einstein's theory of general relativity for very strong fields. It has established the nature of gravitational waves, demonstrated the existence of black holes with masses 30 times that of our Sun, and opened a new window on the universe. Gravitational radiation was predicted 100 years ago by Einstein. They consist of incredibly tiny ripples in the very fabric of 4-dimensional spacetime that emanate from rapidly moving masses and propagate at the speed of light, like ripples on the surface of a pond. Emission of gravitational radiation was inferred from the orbital decay of a single binary pulsar some 30 years ago. But the direct measurement of those tiny space-time ripples required the sustained vision and instrumental ingenuity of Draver, Thorne, and Weiss. When a gravitational wave passes through Earth, it distorts space, alternately stretching it in one dimension and compressing it at right angles. LIGO consists of 2 perpendicular arms, each 4 kilometers long, which respond to this distortion, changing in length by a tiny fraction of the diameter of a proton. Measuring such minuscule displacements is the astonishing technical feat that was accomplished by LIGO. To distinguish the passage of a gravitational wave from noise, LIGO deploys 2 identical interferometers, one in Washington State and the other in Louisiana. When the wave hit the Earth, the 2 instruments registered identical signals. The tiny effect that gravitational waves have on space led many scientists to believe they would be undetectable. In 1972, Rainer Weiss worked out the basic interferometer concept that eventually became LIGO. He provided technical leadership and devoted his extraordinary experimental acumen over the following decades, contributing to every aspect of the final apparatus. Since the 1960s, Kip Thorne had been evaluating how extreme events in the universe, such as colliding black holes and neutron stars, would generate gravitational radiation. In 1975, Thorne and Weiss began discussions of how to build Weiss's interferometer. Thorne provided scientific leadership and the vision that led to the establishment of LIGO. Ronald Draver joined Thorne and Weiss in 1979 as a third founder of the project. Draver applied his experimental genius to perfecting the design and operation of interferometers. His insights led to major improvements in LIGO's capability that were essential in achieving the required sensitivity. The detection of gravitational waves is an achievement for which hundreds of scientists, engineers, and technicians around the world share credit. The ingenuity, intellectual leadership, and sheer tenacity of Draver, Thorne, and Weiss were the driving force behind this epic discovery.
Congratulations to the 9 new Kavli Prize laureates. They have all made breakthrough discoveries providing knowledge that has and will have effects far beyond their fields of investigation. Their contributions stand out as truly excellent and will inspire future generations to use their talents in the pursuit of knowledge. Our society and our culture are built on scientific discoveries, and it is a privilege to honor those who contribute the best. We look forward to seeing you in Oslo on September the 6th for the Kavli Prize Award ceremony.
So there it is, 9 new Kavli Prize laureates for 2016, all celebrating pure scientific research. Many congratulations to all of them. That is it for us here in Oslo at the Academy, but the celebrations will continue over at the World Science Festival in New York, where I understand both Kip Thorne and Rainer Weiss are in the audience. I think you're going to have a very nice day. And for those watching online, the celebrations and discussions will be streamed live from the Kavli Prize website.